The image arrived on a Tuesday. No press release, no live stream, no announcement of any kind. Just a file, compressed and encoded, transmitted across 24 billion kilometers of absolute nothing, from a spacecraft that by all reasonable expectations should have gone silent years ago. The signal traveled for over 22 hours before it reached Earth. It passed through the outer edges of the solar system, through the boundary where the sun's influence finally gives way to interstellar space, through the vast dark between the planets, and finally down through the atmosphere to a receiving dish in the high desert of California. And when the team at NASA's Jet Propulsion Laboratory finally looked at what the data contained, what they saw did not match anything in the models. Not a calibration error, not a sensor artifact. The anomaly was consistent across multiple instruments, across multiple observation windows, across months of accumulated data. It was real, it was stable. Something was happening at the very edge of the solar system. Something that our best models had entirely failed to anticipate. This is the story of what they found. Most people have a mental picture of the solar system that stops somewhere around Neptune. That's where the planets end. That's where the textbook diagrams draw their final circle. It doesn't. Every second of every day, the sun expels a stream of charged particles, protons, electrons, helium nuclei, moving outward in all directions at speeds between 300 and 800 kilometers per second. This is the solar wind. It is not a metaphor. It is a real, physical outflow of matter, billions of tons of it per day. This wind does not stop at Neptune. It keeps going, thinning and slowing as it expands across an ever larger volume of space, but still moving, still carrying the sun's magnetic field with it like a vast invisible net cast across the entire planetary system and far beyond. Eventually, this wind encounters resistance. The space between stars is not empty. It contains the interstellar medium, a diffuse mixture of gas, threaded with magnetic fields and high-energy particles. And as the solar wind expands outward and weakens, it reaches a point where it can no longer push back. That point is called the termination shock. Together, the termination shock, the heliosheath, and the heliopause define the heliosphere, the vast bubble of solar influence that surrounds our entire planetary system. Every probe we have ever launched, every human being who has ever lived, existed inside this bubble. There are two spacecraft at the edge of the solar system right now. Voyager 1 and Voyager 2, both launched in 1977, both still operating, still transmitting, still returning scientific data from distances no other human-made object has ever reached. When Voyager 1 launched in September 1977, the mission objective was straightforward: fly past Jupiter and Saturn. The spacecraft was designed to last 5 years. That didn't happen. Voyager 1 crossed the termination shock in 2004, at a distance of about 94 astronomical units from the Sun. It then spent 8 more years traversing the heliosheath before crossing the heliopause itself. The crossing happened in August 2012. For the first time in human history, one of our instruments was in interstellar space. When scientists compared the heliopause crossing data from Voyager 1 and Voyager 2 to crossings at different points on the heliosphere surface, they found something unexpected. The heliosheath was measurably thinner at Voyager 2's crossing point, in a way the standard models did not explain. That discrepancy sat in the data for years, noted, puzzled over, not resolved. Then New Horizons started sending home its data. The standard model describes the heliosphere as roughly comet-shaped, a blunt leading edge pressing into the interstellar medium, and a long trailing tail, the heliotail, stretching out behind it. Like a bubble moving through water, slightly compressed at the front, elongated at the back. IBEX detected a narrow, bright ribbon of enhanced emission encircling the heliosphere, a ribbon that no model had predicted. A ribbon whose origin took years of debate to partially understand and which is still not fully explained today. What they pointed to was a specific, localized feature on the leading edge of the heliosphere, a region where the boundary was consistently thinner, more compressed, and apparently being pushed inward by something external. The question became, what? The first hypothesis, the solar cycle. A sustained period of reduced solar output could allow the interstellar medium to compress the heliosphere from outside. But after accounting for the full effect of solar cycle variability, a residual compression remained unexplained, stable, present across multiple observation periods. The second hypothesis, the local interstellar cloud. The Sun is moving through a region called the local interstellar cloud, a wisp of partially ionized gas roughly 30 light-years across. The Sun is moving toward its edge. If the external pressure is increasing as we approach a denser region, the heliosphere would compress on its leading edge. The third hypothesis involves the interstellar magnetic field. Where the solar and interstellar magnetic fields interact at the heliopause, the geometry of the boundary is partly determined by the angle between them. A change in the field orientation could reshape the heliosphere in ways the models don't capture. We have almost no direct measurement of the interstellar magnetic field structure. Galactic cosmic rays are charged particles accelerated to extraordinary velocities by supernova explosions, the remnants of dead stars, the jets of active galactic nuclei. They are everywhere in interstellar space, a constant rain of high-energy particles streaming through the galaxy in all directions. And the heliosphere blocks most of them from reaching us. When Voyager 1 crossed the heliopause in 2012, its cosmic ray detector registered a dramatic increase in the flux of galactic cosmic rays. Inside the heliosphere, the cosmic ray flux is suppressed by roughly 50 to 75% compared to interstellar levels. A compressed heliosphere would be a less effective shield on that side. The geometry of the protection would change. Current measurements don't show a detectable increase in cosmic ray flux at Earth's orbit. The anomaly is at the boundary, not propagating inward. The inner solar system, for now, appears unaffected. The Interstellar Mapping and Acceleration Probe IMAP was designed specifically to address the questions that IBEX had opened and the Voyager data had deepened. IMAP launched in 2025. It is stationed at the L1 Lagrange point, approximately 1.5 million kilometers from Earth. From this vantage point, IMAP has an unobstructed view of the full sky. Where IBEX produced rough, pixelated maps, IMAP will produce high-resolution maps that reveal fine structure, texture, asymmetries, localized features that IBEX could not resolve. If the leading-edge compression is a real structural feature, IMAP will map it clearly within the first year of science operations. Beyond IMAP, the community is discussing what a true interstellar probe would look like. A spacecraft designed to travel as fast as possible to the heliopause and beyond, sampling the interstellar medium directly from multiple points. Such a mission would potentially reach the heliopause in 10 to 15 years rather than 35. Step back from the individual pieces and look at what the full picture is telling us. The heliosphere is not behaving the way the standard models predicted. That sentence alone is significant. The anomaly appears independently, in complementary ways, in the Voyager crossing comparison, in the New Horizons particle data, and in the IBEX heliosphere maps. Independent lines of evidence pointing in the same direction is, in science, one of the strongest signals that something real is being observed. Either the models are missing a physical process, or the boundary conditions are different from what the models assume, or the anomaly is not what it appears to be. What we will not learn is nothing. Think about what the Sun has been doing for the past 4.6 billion years. It has been moving, completing one orbit of the galaxy every 225 million years, bobbing above and below the galactic plane on a period of roughly 60 to 70 million years. Throughout all of this motion, the heliosphere has been the Sun's companion. The most discussed encounter is the Sun's passage through the local bubble, a vast cavity carved out by ancient supernovae, roughly 1,000 light-years across. The Sun entered this bubble approximately 5 to 10 million years ago. The transition from denser medium to thin, hot gas would have dramatically changed the heliosphere size. There are geological signatures, elevated concentrations of radioactive isotopes like iron-60 in ancient ocean sediments that appear to record the arrival of supernova debris at Earth. These events, when the heliosphere was compressed by a blast wave, allowed interstellar material to reach the inner solar system and left chemical traces in the geological record. The heliosphere we live in today is not a static, permanent feature. It is a dynamic structure, responsive to its environment, that has looked very different in the past and will look very different in the future. The anomaly we are discussing may be a small perturbation, or it may be the beginning of a more significant change. Return to that Tuesday morning. The file arrives. The data is decoded. The team opens it and sees something that doesn't match the models. In a different era of science, 50 years ago, 100 years ago, that moment would have been the end of the story. The instruments didn't exist to follow up. We are not in that era anymore. The anomaly didn't go into a drawer, it went into a pipeline. This is what modern science looks like at its best. Not a single moment of discovery, but a sustained, coordinated effort across multiple missions, multiple instruments, multiple institutions, and multiple decades. The question of what is pushing on the edge of our solar system touches on the fundamental physics of magnetized plasma. It touches on the structure of the local interstellar medium. It touches on the long-term habitability of Earth, and it touches on our understanding of where we live. We live inside a bubble 120 astronomical units across, maintained by the continuous breath of a star. A bubble that has sheltered life on Earth for hundreds of millions of years. Something is touching the edge of that bubble. Something we didn't predict, something we don't yet fully understand. And for the first time in 50 years of heliospheric science, we have instruments sensitive enough, precise enough, and well-positioned enough to find out what it is. The image arrived on a Tuesday. The answer is still coming, but it is coming.